Hi, George Diamond here again. Now, this is video number 2. When we're looking at the first fundamental theorem of calculus. Now, once again, in my textbook, this is section 4.4. We use the loss in text. Now, video number 1, we talked about the first fundamental theorem of calculus. We just only did one example. We talked about how to find the average value or the average value theorem, okay, for integrals. But in this video now, we're going to look at several examples as to how to actually evaluate a definite integral, how to find area under a curve or between a curve and the x-axis. We're going to do a couple polynomials. We'll do a radical problem or two. We'll do an absolute value. We'll do a trig problem. We'll do several problems as to how to evaluate a definite integral. Now, once again, remember now, if you didn't see the first video, now the fundamental theorem of calculus tells us how to evaluate a definite integral. Now, definite integral is set up like so. This is your integral symbol here. And A is your lower limit, B is your upper limit, okay, of your function f of x. Now, when you evaluate a definite integral, you take the antiderivative at B minus the antiderivative at A. So this was discussed in our first video. Okay, also I'm assuming that everybody, that if you're watching this video, that you already know how to find an antiderivative. Because with these problems now, this is going to be the first step in the problem. Okay, the first thing we got to do, find the antiderivative, and then there's some arithmetic we have to do typically. Right? But this is the fundamental theorem of calculus. The antiderivative of B minus the antiderivative at A. Now, on our first problem, okay, we're going to evaluate each definite integral. And I said our first integral here, we're going to evaluate the definite integral from 1 to 2. Okay, 1 is our lower limit, 2 is our upper limit of a little parabola. Now, this is x squared minus 3 dx. So let's see what we get with this definite for this definite integral here. Now, keep in mind now. Okay, when you evaluate just a simple definite integral, you can get positive answers, you can get negative answers. Now, if you actually have to find area, though, area has to be positive, right? So here we're just evaluating some definite integrals. That's all. Some answers will be positive, some will be negative. So that's not going to be a big deal. So let's start off. First thing you want to do is find the antiderivative of x squared minus 3. Now, to find the antiderivative, we're going to use the power rule for antiderivatives. If you remember the power rule now, we're going to find the antiderivative of x squared, would give us x to the third power divided by 3. So remember, you're going to add 1 to your exponent divided by the exponent plus 1. Now, the antiderivative of 3, so minus, is 3x. So I'm going to put this step in. Now, our lower limit is 1, the upper limit is 2. So we're going to find the antiderivative, which is x cubed over 3. Okay, minus 3x, and we're going to when we evaluate our definite integral, the lower limit is 1, the upper limit is 2. So I'm going to set my problem up like this. This is the middle step here. There's several different ways to demonstrate this middle step, but this is how I do it. All right, now this is our antiderivative. All right, so as you evaluate finish evaluating the definite integral, we've got to take the 2, the upper bound, the upper limit, if you will, substitute it into our antiderivative for x. Minus, then the lower bound substituted into the antiderivative for x. So as we set this up, okay, we'll do brackets, and this is 2 to the third power, so it'll be 1/3 times 2 to the third power minus 3 times 2, okay, minus. All right, so you're going to take the upper bound of your definite integral, right? You're going to take the 2, and you're going to substitute in for every x in your antiderivative, okay, minus. Now we're going to take the lower bound, substitute that in for x. This would be, now x cubed over 3 is the same thing as 1/3 times x cubed. So it'll be 1/3 times 1 to the third power minus 3 times 1. And I'm going to close my brackets. Now, a big caution here when you evaluate a definite integral. Okay, you're going to have a big subtraction here. You know, this is f of b minus f of a. So when you evaluate a definite integral, you're going to end up with a big subtraction. Now, if you're not careful, it's very easy to miss your signs here. In particular, if you have more than one number over here. Right? So you got to be very, very careful with your grouping symbols. So I always start off with the with brackets minus brackets here, but you can set it up however you want to. You can use it, but you do have to be careful with your grouping symbols. So you may have multiple grouping symbols here as you set this up. So this is the antiderivative of b. So that is, you're going to take the upper bound, substitute it into your antiderivative for x, minus the antiderivative at a. So you're going to take the lower bound and substitute that into your antiderivative, and this is going to evaluate the definite integral. Now, if you're just finding the antiderivative is, a function plus c. But now, a definite integral, we're going to get a number. So now we're going to do some arithmetic. Now, if you've got, if your teacher will allow you to use a graphing calculator, some of this arithmetic will go fast. But now, keep in mind, any students, if you have to take the AP Calculus exam, so if you're in high school and you're going to have to take the AP Calculus exam, this type of arithmetic, they're going to expect you to be able to do this arithmetic without a calculator. So if you're using a calculator, that's fine. But if you're a calculus student, if you're taking AP Calculus in high school, this type of arithmetic, they're going to expect you to be able to do by hand. Now let's see what we get. 2 to the third power is 8. 8 times 1/3 is 8/3. So 8/3 minus 6 minus. All right, so I'm going to take this down step by step because I got to be very, very careful. Myself, I got to be very careful because there's a lot of opportunities here for you to miss the sign or to just make a simple arithmetic error. Now, if you're not using a calculator, it's just a matter of time before I make a mistake. So hopefully I'll catch it, but you never know. Now, for the other substitution here, 1/3, 1 cubed is 1 times 1/3 is 1/3. Okay, minus 3 times 1 gives us 3. Okay, and we're taking it down step by step again. Now, next thing I want to do is this, all right? So this will make this a little bit easier. This minus sign in front of this grouping symbols here. I'm going to go ahead and distribute this negative now. I'm going to change this to plus a negative 1/3, and then I'll make that a plus 3. So I'm going to go ahead and change the sign right now. That way I can go ahead and I can ignore my grouping symbols now, and I can just start combining fractions and integers. Now, 8/3 minus 1/3 gives us 7/3. Negative 6 plus 3 gives us negative 3. And we'll write that as negative 3 over 1. So you got 7/3 minus 3 over 1. So let's see if we can evaluate this, get the same denominator here. This is a couple of fractions. Remember, to add and subtract fractions, they got to have the same denominator. So 3 over 1 is the same thing as 9 over 3. So multiply. 7/3 minus 9/3 now is going to give us a negative 2/3. So as we evaluate that first definite integral there, the area between the curve and the x-axis, or just the definite integral, would be negative 2/3. Not really an area, but this would be the answer to our definite integral. From 1 to 2 would be negative 2/3. Okay, let's try another example here. This is our first problem. And once again, we're just evaluating each definite integral here. So let's try another one. I want to erase here to give myself lots of room. All right, so let's try another one. Erase this. Okay, now we've done it. Right. Now, the first problem was just a little polynomial. So let me take a look at, let's see what the next one was. Let's try one involving a radical. Right, so let's see if we can evaluate this definite integral here. So problem number 2. Okay, this time let's see if we can evaluate this definite integral. Now we're going to do the integral so we integrate from 1 to 4. So 1 to 4 of 3 times the square root of x dx. Let's try this definite integral here. Now first of all, the square root of x, let's rewrite this. This will be the integral from 1 to 4, 3 times x to the 1/2 power dx. All right. Now remember, when you evaluate a definite, when you evaluate, you find the antiderivative, we need to see the exponent. All right, so convert from radical notation to fractional, to your fractional exponent, to your rational exponent, if you will. Okay, now let's go ahead and get our antiderivative. Now the antiderivative of 3x to the 1/2 would be 3 times. So 3 times. Now to find the antiderivative of x to the 1/2 would be, remember now, you're going to add 1 to your exponent, right? That's going to give us x to the 3/2 power divided by 3/2. Right, so this is going to be our antiderivative, and once again, we're going to evaluate from 1 to 4. Right. Now, let's see if we can simplify the antiderivative just a little bit here. So let's bring this down. This will be 3 times. Now, x to the 3/2 power divided by 3/2 is the same thing as 3 times 2 over 3, x to the 3/2 from 1 to 4. Now the 3's are going to cancel out, so this will simplify then as 2x to the 3/2 power from 1 to 4. Right. So let's go ahead and simplify the antiderivative. It'll basically make things a lot easier as we evaluate the definite integral. So simplify your antiderivative. And okay, we've got 2x to the 3 power. All right. So for our antiderivative, now the next step is to substitute the upper bound and minus the lower bound. All right. So let's do the 4 first. So as you substitute this in, this will be 2 times 4 to the 3 power minus, and once again I'm putting the first substitution in grouping symbols in brackets, right, minus the second substitution, substitute the lower bound now. This will be 2 times 1 to the 3 power. So substitute the upper bound minus the lower bound. Once again, this would be f of b as you look at the theorem minus the antiderivative of a. So when you make that substitution, this is what we're evaluating now. So we're going to do a little bit of arithmetic now. Let's do the 2, 4 to the 3 power. Now first, 4 to the 3 power, I'm going to do the square root first. So the square root of 4 is 2, 2 to the 3rd power is 8. 8 times 2 gives you 16. So this one we'll evaluate as 16. Now the square root of 1 is 1. 1 cubed is 1 times 2 gives you 2. All right, so our definite integral should evaluate as 16 minus 2 or 14. So there you go. There's a little radical problem. Okay, that wasn't too bad. That wasn't too bad. Let's try a trig problem. Let's try a trig problem. Okay. So let's try a trig problem. Now as we do this first trig definite integral, my students, if they've watched the my videos on antiderivatives. Okay, you need to have memorized the 6 antiderivatives for your 6 trig functions. All right, so you don't want to have to think about those. Those should pretty much be automatic. So let's start off with this first problem. This first trig problem. This is problem number 3. Okay, we're going to integrate or find the antiderivative from 0 to power 4 of secant squared of x dx. So let's try this definite integral here. Right. So the antiderivative from 0 to power 4 secant squared x dx. So now the first step is to find the antiderivative of secant squared. Now, right away you should recognize the antiderivative of secant squared is tangent. So this is tangent x from 0 to power 4. So we get your antiderivative. Now we're ready to substitute the upper bound minus the lower bound. So let's substitute power 4 in for x first. Okay, this would be tangent power 4. Once again, I'll put this in brackets. And I want you to kind of get into the habit of using these grouping symbols, all right? Because with a little problem like this, the grouping symbols aren't that important. But if you're working with polynomials and things, you have to make sure you get these grouping symbols in, because it's very easy. If you don't put these grouping symbols in, particularly after the subtraction here, you're going to get sign errors, right? So now we substitute the power 4 in minus tangent 0. Right. Now, as you're evaluating tangent power 4, now tangent power 4 is 1 minus, now tangent 0 is 0, right? So the antiderivative at power 4 is 1, and 1 minus 0 gives you 1. Okay, that's going to be our antiderivative here. Right, so that wasn't too bad, just a little trig problem. Now, let's try another radical problem. This problem's a little bit more difficult. This one's pretty easy. Let's try one that requires a little bit of simplification now. Let's try this right here. This is problem number 4. And this time we're going to integrate this problem from 0 to 4. So from 0 to 4, and this time we'll do x minus 2 over the square root of x dx. So let's try this problem here. Let's try one that requires a little bit of simplification. All right. So as you look at this integral, the way it's set up, okay, this is a fraction. This is a quotient. Now remember, we don't have a quotient rule for integration. We have one for derivatives, but we do not have a quotient rule for integration. We're going to have to see the exponent. That means with this type of problem here, it's going to require some simplification. So to get started, we simplify this now. This will be from 0 to 4. Now first of all, the square root of x, let's rewrite this. This will be x minus 2 over x to the 1/2 power dx. Okay. Now to simplify this a little bit further, we got a binomial divided by x to the 1/2 power. Let's divide x to the 1/2 power into both terms in our numerator here. So this will simplify then as 0 to 4. Okay, x over x to the 1/2 minus 2 over x to the 1/2 dx. So let's take the x and the minus 2, divide each of them by x to the 1/2 power. Okay, now one thing about these types of problems, these definite integrals, they can take a lot of space. I got a pretty good marker board here, but even then, some of these really long problems, and I may have to erase part of it to get to finish the problem in some cases. Now, to simplify x over x to the 1/2, remember when you divide terms that have the same base, you subtract your exponents. So 1 minus 1/2 gives us x to the 1/2. So as we simplify this a little bit further, it'll be from 0 to 4. It'll be x to the 1/2 power minus. So x to the first divided by x to the 1/2. 1 minus 1/2 gives you x to the 1/2 power. Now, 2 over x to the 1/2. Remember, you can pull the 2 off. That's the same thing as 2 times x to the negative 1/2 power. So if we simplify the 2 over x to the 1/2, that's going to be 2x to the negative 1/2 power dx. Okay. All right. Now, with this problem, probably the hardest part of this problem for a lot of students is going to be simplifying it down to here, so we can go ahead and find the actual antiderivatives. But like I said, you got to be able to see those exponents. We do not have a quotient rule for integration. So if you have this fraction here, you're going to have to rewrite it and do some simplification before you can actually do this problem. Now let's find the antiderivative of each of these terms here. So let's do the antiderivative of x to the 1/2 first. Now that will give us, once again, you're going to add 1 to your exponent. 1/2 plus 1 will be x to the 3/2 divided by 3/2. So x to the 3/2 power divided by 3/2 minus, this will be 2 times. Now once again, we're going to add 1 to your exponent. Negative 1/2 plus 1 will give us a positive 1/2. So it'll be x to the 1/2 power divided by 1/2. And once again, we're integrating from 0 to 4. All right. Now, let's simplify this a little bit, and then we'll go ahead and make our substitutions. All right, so x to the 3/2 divided by 3/2. Remember, as you simplify here, this will be 2/3 x to the 3/2 power. X to the 3/2 divided by 3 over 2. Okay, that's multiplied by the reciprocal of that bottom fraction. If you're dividing by 3 over 2 or 3/2, that's the same thing as multiplying by 2 over 3. So we're going to rewrite that as 2/3 x to the 3/2 power minus. And then as we simplify here, this will be x to the 1/2 divided by 1/2. You're multiplying by 2 over 1. So that'll simplify as 4 x to the 1/2 power. And once again, we're integrating from 0 to 4. Okay. All right, so we've got our antiderivative. We got it pretty much simplified now. Okay, now I think we're ready to go ahead and do our substitution. So let's substitute the upper bound minus the lower bound. All right, so as we simplify here, this will be 2/3. And we'll put this in brackets, so 2/3. Now we're going to take the 4, substitute the 4 in for each x in your antiderivative. So it'll be 4 to the 3/2 power minus 4 times 4 to the 1/2 power minus. Now remember, this is the antiderivative at b minus. Now let's take the lower bound, which is 0, substitute this in. So it'll be 2/3 times 0 to the 3/2 power minus 4 times 0 to the 1/2 power. Now this is all 0 here, so I'm going to cross this out and put 0. All right, so that's all 0. So this is f of b minus the antiderivative of a. So the antiderivative of b minus the antiderivative of a. You substitute the upper bound into your antiderivative minus the lower bound substituted into the antiderivative. Now let's see what we get here for our antiderivative. So to begin, let's do the 4 to the 3/2 power. Now to begin with, the square root of 4 is 2. 2 cubed gives us, 2 to the 3rd power gives us 8. 8 times 2 is 16, so it'll be 16 over 3 minus. So minus. 4 to the 1/2 power is the same thing as the square root of 4. So the square root of 4 is 2. 2 times 4 gives us 8. Minus. And this is all 0 here. So this is 16 over 3 minus 8, which would be 16 over 3 minus this 8 over 1. So that would be 24 over 3, which will evaluate as, so 16 over 3 minus 24 over 3. You write that a little bit better here. So 16 over 3 minus 24 over 3 will give us a negative 8/3. So that's the antiderivative, that's the definite integral from 0 to 4 of this expression here with that radical in it. Right, so that was, hopefully you found that one helpful. So that's just kind of looking at some of the homework problems that my students have to do. This would have been one of the harder problems. A lot of my students would have had trouble with this problem right here because you're going to have to simplify it first. Several steps there you have to simplify. Okay, now let's try an area problem now. So these are just just finding, just evaluating definite integrals. Okay, let's try an actual area problem now. And now with this area problem, let's make this one a. So let's make this one an absolute value problem. All right, so we've not done one of those yet. So let's try some absolute value problem. Okay. Let's see, this is problem number 5. And once again, we're going to find the area from 0 to 2. We'll use this integral here. Go from 0 to 2. An absolute value of 2x minus 1 dx. We'll do an absolute value problem, and we're going to write it up as an area. So finding the area now, this should end up as with a positive answer, right? Because we're actually looking for the area of this problem. Now, first of all, just if you can imagine, let's imagine the what this graph is going to look like now. Now, first of all, you got 2x minus 1 is your absolute value. So if you take 2x minus 1, set that equals 0. If 2x is equal to 1, x is equal to 1/2. So if you can imagine the graph of this function, this is an absolute value function, so you're going to have something like this right here. So here this would be 1, this is 1/2 here. So if you were to imagine, if you can imagine the graph of this function, okay, it's going to do something like this. It's going to look like that. So now here's 2. So if you can imagine the region that we're trying to find the area of, right? So bringing up our curve here. So if you can imagine this region here, this region right here. Okay, this is the area we're trying to find the area of. So as you look at this absolute value function, this can get that V shape, and that V shape should be the vertex here of your V shape of 1/2. So at the 2x minus 1 equals 0, by setting that equals 0 there, you can find where the slope is going to change and you get that V shape. All right, so as we set this up, now, one thing we're going to have to do here, which is kind of different, so as we, in order to evaluate or find the area between the curve and the x-axis here, okay, we have to divide this up into 2 integrals. We're going to do one integral from 0 to 1/2, and then we'll do another integral from 1/2 to 2. All right, so we'll have to set this up. So we'll do two integrals. All right, so we have to find the area of this region, and then the other area, the area of the other region here, right? So as we calculate our area. Now, if you can imagine, if you look at your absolute value here, so the absolute value of 2x minus 1 is equivalent to, you can imagine this is a step function. Okay, first of all, coming from the left-hand direction, you have the opposite of 2x minus 1. For x is less than 1/2. Okay, so you got the left-hand side, which is this linear function here. And then you got the right-hand side, which is just 2x minus 1, for x is greater than or equal to 1/2. So if you look at this absolute value function, you've got the left-hand part and the right-hand part. Okay, the left-hand part has a negative slope, and the right-hand part has the positive slope. Okay, so now I'm going to distribute this negative here, make this a negative, that'll be a plus there, so it'll be a negative 2x plus 1 as I set this up. So in order to find the area from 0 to 2 of this absolute value function now, I'm going to set this up as 2 separate integrals, right, and then add them together. Now the first integral will go from 0 to 1/2, so 0 to 1/2. Using the left-hand side of the absolute value here. So it'll be negative 2x plus 1 dx plus. That's the left-hand side of the V shape, if you remember from our graph. then plus. Now the other part of the integral will be from 1/2 to 2. So 1/2 to 2, and this time we're going to use the right-hand side. This will be 2x minus 1 dx. So we're going to separate this and divide this into two separate integrals, and we're going to find the area of each region and add them together. All right, now this is going to be a pretty good little problem as we set it up, because we're working with not just we have not just two substitutions, we have 4 substitutions here, working with the two separate integrals. So let's find our antiderivatives. Erase this part here. And like I said, with this type of problem here, it's going to be kind of a long problem. So let's start off. Let's find the antiderivative of the negative 2x plus 1. Right, of our first integral here. Right, so finding the antiderivative of negative 2x. Now remember, the antiderivative of negative 2x plus 1. You're finding the antiderivative would be dx, and you're finding this antiderivative would be negative 2 times x squared over 2 plus 2x. Now, so finding the antiderivative again, now these will cancel out, we'll give you negative x squared. So negative x squared, and let's see, negative 2, and let's see, negative 2. So we need to see this parentheses here, right? So not the plus 2x. So it'll be negative x squared plus 2x, or just be plus x, I'm sorry, not 2x, it would just be plus x, or 1x. So it'd be negative x squared plus x would be our antiderivative. So evaluating this first antiderivative now would be negative x squared, okay, plus x, and that'll be from 0 to 1/2. All right, so that's that first antiderivative there. All right, now let's try the other antiderivative. Let's find the antiderivative of 2x minus 1. So we're going to find the antiderivative here of 2x minus 1, okay, dx. All right, now I'm going to erase this in just a second, so kind of save a little bit of space here on my marker board. Now the antiderivative of 2x would be 2 times x squared over 2 minus 1x. Now here the 2's are going to cancel out, it just gives us x squared minus x. All right, so it'll be the antiderivative of the integral from negative x squared plus x, 1/2 to 0 would be our upper and lower bound. Okay, plus the antiderivative here would be x squared minus x from 1/2 to 2. All right, now I'm going to go ahead and I'm going to erase this. All right, now we're ready to start making our substitutions. Okay, let's evaluate this first integral now. We're going to substitute the 1/2 in for x and then the 0. All right, so as we set this up, I'm going to use brackets again. Substituting the upper bound in would be a negative 1/2 squared plus 1/2 minus, now substitute the 0 in. So minus, this would be negative 0 squared plus 0, which is all going to be 0. Okay, plus, now this is our first integral. So substitute the upper bound minus the lower bound, so substitute the 1/2 in for x first, and then substitute the 0 in, right, and you're subtracting there. Now let's do this. Let's do the second integral now. So substitute the 2 in for x, give us 2 squared minus 2, okay, brackets, minus. So minus, now let's substitute the 1/2 in for x, so it'll be minus 1/2 squared minus 1/2. All right, so here you go. Okay, you get the f of b minus f of a. Okay, this is the first integral, and then you got f of b minus f of a. Okay, this is from our second integral. All right, and then at the end now, so at the end, we're going to add the two together, and this will give us the total area. So let's see what we get. So we've got to do a little bit of arithmetic now. Now I got to kind of. Now myself, I have to take this out step by step, because if you try to do too much in my head, or you start leaving out steps, invariably I'll miss something. Right? So when you're doing a arithmetic like this, it's very easy to miss a sign, or to just do a little arithmetic area. Okay, first of all, negative 1/2 squared. 1/2 squared would be 1/4, so evaluating this would be 1/4 plus 1/2. Okay, minus 0. So minus 0 plus. Let's see, 2 squared would be 4 minus 2 minus. Now 1/2 squared would be And I also want to go ahead and distribute this negative to both of these terms here. So it'll be plus a negative here, and that becomes a plus 1/2. Now, if you're not careful, you have to be very, very careful with these grouping symbols here. That minus sign in front of your brackets is going to change the signs on the 1/2 squared and the 1/2. Come from a minus 1/2 to a plus 1/2. So you got to change the signs there. Now this becomes plus, and this will be not being a minus now actually. This will be minus 1/4 plus 1/2 now. Okay. Let's see now the 0 here. We can discount that. And let's see now. Let's go through. We've got a couple things that we can start adding here. Okay. Let's start off with negative 1/4. And negative 1/4. Let's add the two negative fractions together. Now, negative 1/4 plus negative 1/4 is going to give us negative 2/4, which is negative 1/2. So negative 1/2. So when you add the negative 1/4 and the negative 1/4 together, that's going to give us negative 1/2. Now let's add the 1/2 and the 1/2 together. Okay, that's going to be 1. So it'll be negative 1/2 plus 1. Erase this here. So plus 1. 4 minus 2 gives us, 4 minus 2 is 2, so it'll be plus 2. Okay, now plus 2 is 3, so it'll be negative 1/2 plus 3. Now adding negative 1/2 and 3 together would give us, so it'll be negative 1/2 plus, and this would be 6 over 2, which would be 5 over 2. So the area, now this would be in units squared. So we're looking for area this time. So it'll be 5 halves units squared. So now that was a pretty good little problem. You got to be very careful because with the absolute value here, you have to find out where the vertex of that V would be. And you're going to have to do the left-hand side and the right-hand side separately and add them together. Now, if you did this on a graphing calculator, you can go to the absolute value function on your graphing calculator, and this can be done much, much faster, very quickly using a graphing calculator. But this is, I want to do one absolute value example. This is a pretty good one. Now, my students, when they get to their homework part, there's a couple of absolute value definite integrals that they're going to be asked to do. And I teach AP Calculus in high school, so it's very possible, when they take the AP Calculus exam, that they can run into this type of problem. We've got to divide it up into two different intervals, so like so. Now, for our next problem, let's try an average value problem. Now, some average value. Erase this. So let's try an average value problem. All right, so average value. Now, we talked about average value on our first video. All right, so as we set this up, let's see if we can find the average value this time. And let's see, this is problem number 6, I believe. So find the average value. So the average value, of y equals 3x squared minus 2x. So minus 2x. On the interval from 1 to 4. All right. Now, if you didn't get to see my first video, now remember, average value is gotten by doing 1 over b minus a, integral from a to b, f of x dx. All right, so when you do average value, this is when you do average value. All right, and remember now, when you look at average value, this is equivalent to, if you can imagine, when you calculate average value or you determine average value, if you can imagine a curve. So if you can imagine a curve from A to B. So if you can imagine a curve from A to B, and you're calculating the area under that curve. Now what the average value will give you, it will give you the height of a rectangular region that has the same area as this region here, from A to B. Okay, this is what the average value will give you. So if you can imagine, a rectangle, sort of like so, it would look sort of like this right here. And it's going to give you this value right here, f of c, right? So it's going to give you what would be the height of a rectangle that has the same area as the area between the curve and the x-axis, All right? So this is what the average value is going to give us here. So let's see what we get. Now this problem, we need to set up our integral first. Okay, so as we set this up, it'll be 1 over b minus a, so the integral we're integrating from 1 to 4. So it'll be 1 over 4 minus 1 integral 1 to 4. So as you start your integral out, this is how we're going to start it off. So 1 is your lower bound, 4 is your upper bound, so it'll be 1 over 4 minus 1. Okay, divided by, or times the integral from 1 to 4 of 3x squared. So 3x squared minus 2x dx. All right, and so let's start off. Let's see if we can get our antiderivative first. Now 1 over 4 minus 1 is 1/3. It's going to be 1/3 times. Now let's get the antiderivative of 3x squared. Now the antiderivative of 3x squared would be 3 times x to the 3rd power divided by 3. The 3's will cancel out, and that gives us x to the 3rd power. So it'll be x to the 3rd. So the antiderivative of 3x squared is x to the 3rd. So remember, you're going to add 1 to your exponent divided by the exponent plus 1. Now let's do the antiderivative of negative 2x. So the antiderivative of negative 2x, this will be x squared over 2 times negative 2. And once again, you're going to add 1 to your exponent divided by the exponent plus 1. These will cancel out and it gives us minus x squared. So it'll be minus x squared from 1 to 4. Okay, now we've got our antiderivative, and we're going to do this just like we did the other problems. We're going to evaluate the definite integral and then times 1/3. All right, so whatever we get, we have to multiply times 1/3. So after we, so let's see. To start off, we're ready to make our substitution. This is our antiderivative from 1 to 4. Let's substitute the 1/4 in. So we're going to have now 1/3 times. Now, our first substitution, let's substitute the upper bound in first. That will be 4 to the 3rd power minus 4 squared. Minus, now let's substitute the lower bound in. And this will be 1 to the 3rd power minus 1 squared. And this is the antiderivative of b minus the antiderivative of a. So this is the fundamental theorem of calculus in action. You see this, so the antiderivative of b minus the antiderivative at a, and we got to remember to multiply by 1/3. Now, one thing I like to do, as I set my problem up, I like to make sure I have that 1/3 down, that 1/3 in at the beginning of the problem. So I can remember at the end of the problem, I got to multiply by 1/3. Right? So some students will wait to the end of the problem to try to multiply by 1/3. By that time, you've forgotten about the 1/3. So I like to keep it, I like to break it down step by step. Right, so as we evaluate this, let's see what we get now. 4 to the 3rd power will be 64 minus 16 times 1/3 minus 1 minus 1. Now 1 minus 1 is 0, right? So this is 0. So now we've got 64 minus 16, which is 48, times 1/3, which is 16. So there you go. The average value is 16. Now this was a parabola. So this is a parabola. This is 3x squared minus 2x. So if you can imagine this function here, the graph, this particular graph, so this would be a parabola. So let me show you what it is that we've just found. So this is a parabola of some type. So let's see, when x is 1, y would be 1. So from 1 to 4, one point on the curve would be 1.11, and I assume that the other point on the curve would be way up here somewhere. So if you were to look at this parabola, it would look like this. So when you evaluate the definite integral now, just the definite integral would give you the area of this between the curve and the x-axis. Now what we found here, we found 16. Now 16 would be the height of a rectangle. Remember, the height of a rectangle that has the same area as this region right here. So if you can imagine this would look, now this is just an estimation, of course, so sort of like this. So if you can imagine this rectangle, that rectangle there, imagine that this has the same area as the original area between the curve and the x-axis now. What we got this number here. Okay, we got what would be the height of that rectangle. So 16 times 4 minus 1. Now, so if you look at this, if you think about it, the area of a rectangle, so the area of a rectangle is base times the height, right? The height is 16, so it'd be 16. So the base would be 4 minus 1. Right? So it'd be 4 minus 1 times 16, or 3 times 16, which is 48. And the original, the integral itself is 48. And then that gives you the, so that would be the equivalent area. So if the height of that rectangle is 16, it'd be 16 times 3, which is 48. And 48 is actually the area of the, between the curve and the x-axis of the original function. But this is an average value problem over the integral from 1 to 4. So basically, you're doing the same thing, you just have that extra step. You got to remember to in this case, multiply by the upper bound minus 1 divided by the upper bound minus the lower bound. Okay, now we got one more problem. So I hope, thank you for sticking with me here. We got one more problem. Now with this problem, I'm going to kind of set this up a little bit differently. This is problem number 7. And with this problem, we're going to find another area problem. I'm going to set this up as an area problem again. Okay, now let's see, this is problem number 7, I believe. And we're going to find the area of this region right here. Now I'm going to set this up like so. So if you can imagine, here's my curve. So 1 to 2. And let's see, this would be pi over 2 here, pi over 4 here. All right. Now if you look at my curve here, so my curve is going to go like so. So 1 and 2. It's like this. Now if you look at this graph here, this is the graph of y equals 2 cosine x. So this is my region. Now this time, let's see if we can find the area of this region here. Now the reason I want to do this problem here, because when my students do their homework, there's several problems in their homework, and my students will have to set up their own integral. So all they'll have is the graph and the function. So as you look at this particular region now, so I'm on this region here. So you look at this region, you're talking about the area from 0 to 1/2, or to pi over 2. Okay, 0 is this is your lower bound. And pi over 2 is the upper bound. So the upper bound. And this is pi over 2. A little bit better, so pi over 2. So 0 is going to be the lower bound, pi over 2 is the upper bound. Let's write our own integral this time. So we set this up. So our area is going to be equal to the region from 0 to pi over 2. And I said we're going to set this up. This is another trig problem, and my students tend to have more problems. There's some problems with trig problems than maybe these little polynomial problems that they can do. Of 2 cosine x dx. Right. Now, evaluating this integral will give me the area between the curve and the x-axis. Now, keep in mind now, we're calculating area. This should be positive. So the problem says, find the area. It should be positive. Technically, area can't be negative, even though some of the definite integrals here that we've been evaluating have negative answers. But now if you're looking for area should be positive. Okay. Now you can see how we're set up. This is what we're going to look for now. So to get started, now remember now, as we calculate this, we find our antiderivative. We can rewrite this here, this little property of the definite integrals. We can pull that 2 outside the integral of 0 to pi over 2 cosine x dx. So we can pull that we can pull the 2 off that cosine. And if you remember now, you should have these trig functions memorized. Now the derivative of sine is cosine, so the antiderivative of cosine would be sine. So as we calculate our antiderivative now, this would be 2 sine x from 0 to pi over 2. Okay. And let's see what we get. Once again, substitute the upper bound minus the lower bound in, and let's see how we evaluate this. It would be 2 times sine pi over 2 minus, substitute the lower bound in for x now, gives us 2 sine 0. Okay, so 2 sine 0. Now if you remember, sine pi over 2, if you remember your unit circle now, sketch it here, pi over 2 is here, right? And it has a coordinate of 0, 1. Remember, 0 is cosine, 1 is sine. So when you're evaluating sine pi over 2, you have to know, if you know your unit circle, these are really, really simple. Okay, this first is going to be 2 times 1. Now, sine 0, 0 is down here, so be at 0, 0, 1. Now this time, sine is 1. So it'll be 2 times 1 minus. So 2 times 1 minus 2 times 0. So sine 0 will be 0, so times 0. Okay, or 2 minus 0, or 2. All right, now this will be 2 units squared. So these would be 2 Cartesian units squared. So this would be, so with this particular problem now, this kind of, we had the graph, we were given the actual function. So to set up our integral now from the graph, 0 is your lower bound, pi over 2 is your upper bound of your integral dx. That'll give you the area between the curve and the x-axis when you evaluate this definite integral. Okay. Now, hopefully you've found some of these examples of the first fundamental theorem of calculus helpful. There'll be another video coming along in which we look at the second fundamental theorem of calculus, but this will here be a good start.